Everyone's here? Okay, class. Can you see the document?
Yes.
Okay, thanks.
Okay, okay.
Okay, so we're done with this nuclear. We're done with this nuclear. So what are the things you learn under nuclear? Okay, let's be a small recap. So we learn about mass defect, binding energy, and radioactivity decay. E equals mc squared, mass defect, and we learn about what is 1U stands for. Then we learn about binding energy. Okay, the difference, the amount of energy required to remove all the nucleons from the nucleus to infinity. Okay, total energy required. Then we talk about this important graph. Iron, you have to remember the nuclear number is 56. Okay. Then finally, we learn about radioactive decay. 3 unique formula has been developed. All the formulas start with activity proportional to the number of particles. Activity proportional to number of particles. So first equation has been obtained, A equals lambda n. Please ignore the negative. Please ignore the negative. And second equation was developed by using the first equation. This 4 equation has been developed. And be careful, must be the one still haven't decayed, undecayed particle, and the lambda t must be same unit. Okay, A equals to lambda n. This lambda must be in per second. Remember, Then we talk about something called decay constant. Decay constant is the probability for an individual nucleus to decay per unit time. A very important definition they will ask for an example. If the decay constant is huge, then we say the half-life is small. Then we say it's a very very radioactive substance. Okay. So half-life, we talk about half-life, a new formula. So T half is ln 2 over lambda. Okay, so let's do some passes today. My plan is just 2 questions today. Okay. Sorry. Okay, so we go selective questions. Selective questions. Maybe we can start with the page 3. Okay, I need your input for these questions. Okay, the first question. Look at the question. Read the question. Strontium-90 decays with the emission of beta particle to form a yttrium. 90. The reaction is represented by the equation of this. This is the equation. Strontium converted to yttrium plus beta negative decay. This is the energy released. 0.55 mega eV has been released. Okay, the decay constant is 0.025 per year. So they given per year. So suggest with the reason with nucleus, strontium or yttrium has a greater binding energy. Okay, what's your answer? Strontium or yttrium has greater binding energy. Okay. Anybody? Marwan? What's your answer? Any idea? How to know which is stable? How to know
it's more stable?
Why is more stable? Why?
Because it's the product.
Is it product always stable?
Not always, but like
yeah. Not always. But here in this, what evidence shows that?
Oh, okay. Wait, it's endothermic. Wait, it's endothermic.
It's an exothermic.
Oh, exothermic. Oh, exothermic. Okay, I thought it was.
In chemistry you put negative. Here plus 0.55 mega means energy has been released. So yes, correct. So yttrium is found to be more stable than strontium because there is a net energy released.
Yes.
in this process. There is a net energy release in this process. That means some mass has been converted to energy. So the product is more stable than the reactant. Okay, so yttrium is more stable than strontium. Tell me, strontium or yttrium must have a greater decay constant. Iman, yeah? Iman? Iman? Iman, yeah? Okay, Iman, not yeah. Okay. Shike, what do you think? Which has a greater decay constant?
Yttrium.
Yttrium has a greater decay. Yttrium has a greater decay constant.
Oh, sorry. Decay constant is strontium.
Strontium has the highest decay constant. Why? Because unstable. More unstable. Correct. Good. Okay, next, explain what is meant by decay constant. Okay, Shinho, yeah. Shinho, what is meant by decay constant? 2 marks. What is decay constant? Shinho? It's what? It's a probability for a nucleus to decay per unit time. Okay, the probability for a nucleus to decay per unit time. Okay, good. Next, C. At the time of purchase, the strontium 90 source activity is 3.7 times 10 to the power of 6 becquerel. Calculate the sample strontium its initial number of atom. Okay, what formula do you use? This activity of strontium got what is the initial number of atom it has? Atom, they want atom. So what formula do you use? A equals to lambda n, right? We can find the number of atom. Activity, do you know? You know the activity. Activity is 3 times 10 to the power of 6. And you know lambda? Okay, lambda. Give lambda. This is for decay constant for strontium. Is it strontium? Strontium, yeah. So we know the lambda 0.025. Can we write 0.025 here? We can't, right? Because it's per year. Lambda is much. Lambda is per year. So what do you have to do? Convert to per second. How do you convert per second? Times or divide? Times or divide?
Divide.
Divide by, of course, 365 days times 24 times 60 times 60. Change to second. Get your lambda first in per second, then n. Okay, that's a trap. Lambda must be always per second when you use a equals to lambda n. Okay, whenever you use a equals to lambda n. Okay, so then you get an answer. Okay, good. So number of atom can be obtained. Now, just calculation. Okay, next. The initial mass. What is the original mass? You know the number of atom. This atom consists of how much of mass?
You need to know the molar mass.
Okay, molar mass how much? Whatever answer beside, right? Strontium 90 means. So in math, strontium 90 means 1 mole is consider 90 gram. Okay, the nuclear number lah. The nuclear number. Okay, the nuclear number in gram is 1 mole of that substance mass. Okay, so most chemistry knowledge. 1 mole consists of how many atom? How many particle? 6.02 times 10 to the power of 23 particle is 90 gram. So n particle, how many gram? Okay, we want to find that. So by using these two, your ratio, right?
Yes.
So how much the x value? X value is equals to n over 6.02 times 10 to the power of 23 times 90 gram. So you get the answer in terms of gram. So yeah, remember the mole concept, how mole change to mass, how mole change to number of particle, you should know. Mole to change times is a relative atomic mass, right? RAM or RMM. Multiply, or the nuclear number in gram is your mass. A mole to number of particles, just multiply by the Avogadro constant. Okay. So next. Okay, now we know, assume the mass, we know the number of particle. Now the two. Determine the activity A of the sample 5 years after purchase. Expressing the answer as a fraction of the initial A naught. So they're actually asking for A or A naught. Whenever the A or A naught, what formula comes to your mind? A equals to A naught E negative lambda T, of course, right? So you're looking for A over A naught. The fraction of still remain, be careful. It still remain, expressing the answer as a fraction of the initial. Determine the activity of the sample. So the activity at that moment. So A. Of course. E equals negative lambda T, E negative lambda, lambda just now in per year. Okay, so we put per year, time was 5 years. So we just no need to convert 5 years. Lambda is how much? Lambda also in year 0.025. So we put just 0.025. So no need to convert. No need to convert both in years. This is per year. This is year. Save time. Don't convert to second. So you get the answer. Ratio. The ratio of activity still available compared to the original activity. Okay. Any questions, guys? Working?
Teacher, the ratio we write in decimal place or?
Always the answer in Cambridge they give in 3 significant or 2 significant or 3 significant figure of decimal place.
Even
decimal
for ratio.
Yeah, even for ratio also they give decimal place. So 2 or 3 SF. But check your values here. All are 2 SF, right? So I think most of the time the answer will be in 2 SF lah. Okay, the least significant, but one extra allow 3 SF. Yeah. So you give decimal place for ratio. Okay. Okay, next, let's continue. Finding any nucleon of nucleon, a curve is given. We have seen that. The peak is what? The peak is iron 56. 56 iron. Okay. So I think we done this, right? Have we done this? I think we done this, right? Tell the positions. Energy we done? Yeah. Energy, we don't think so. We done. Okay, so we go for part B. Part B we done. Part B1 we done, just plotting the position of the particles. Okay, next, the binding energy per nucleon on each nucleus is given. Uranium, barium, krypton given. Uranium is the reactant. Barium, krypton is the product. We have few neutrons. Okay, chain reaction, right? Chain reaction. So use this data to calculate the energy release in the fission reaction. How much is the energy release in the fission reaction? So energy release in the fission reaction. Yeah, 2 ways to do, right? MC squared or by using the binding energy. But I don't think so we can use MC squared here because mass not given in 5 or 6 decimal places. So we have to use the binding energy. So which binding energy minus which binding energy? Anyone? Energy release. So how do you get the energy release? Energy of
minus the reactant.
Product. Yes, good. Product minus the binding energy of the binding energy of the reactant. Product minus reactant. Okay. If you use E equals to mc squared, the mass defect is mass of the reactant minus mass of the product, C squared. For naturally occurring nuclear process. For exothermic, case of exothermic, yeah, reactant minus product. So be careful. Okay, so you get the answer, energy release. The energy of product, how do you calculate? Go up, energy of product is which one? Barium and the krypton. So barium was this much of energy This is the binding energy per nucleon. Remember, it's per nucleon. So what do you have to do? So this energy only for one nucleon multiplied by how much? The nucleon number, 144, and krypton, the energy per nucleon of krypton multiplied by how much? 90. And don't go use proton, must use nucleon number. Okay, these two energy add up. Okay, you add them, you get the total energy of product, binding energy of product, and reactant is only the uranium. Okay, so the product is the energy of krypton plus the what? Krypton plus the barium. Okay, krypton plus the barium minus the uranium. So you get the energy in joules. Okay. So next, the mass equivalent of this energy. The energy release equivalent to how much of mass? So of course, the formula is what? E equals to mc squared. Whatever energy you got placed here equals to mc squared. You get the mass defect. Okay. Energy, when you use E equals to mc squared, make sure the energy is in terms of joule. Joule, and mass you will get in terms of kilogram. SI unit. Okay. Okay, next. Suggest why the neutron were not included in your calculations. So what's the answer? Why? Why neutron is not included? Because neutron don't have any binding energy. Binding energy, neutron does not consist of binding energy because it's a single particle. It's single particle. It's a single particle, so don't possess any binding energy because it doesn't bind with anything. So therefore not included in this calculation. But be careful, if you want to find energy released by using mc squared, you include the neutron mass or you exclude the neutron mass? Include the neutron mass. All mass counted. That means total mass of the reactant, which is uranium plus the neutron, minus the total mass of the reactant product. Barium, krypton, the mass of 2 times neutron mass also included. Remember, find the mass defect. Okay, so that's the question.
Teacher, if it's an alpha particle, do we need to consider the binding energy?
Yeah, you have to consider. Okay. If it's a alpha particle, yes, alpha particle also has binding energy because it's formed. Okay. Okay, next, November 4. So isotope of radium-224, 226, both undergo spontaneous alpha particle decay. The energy of the alpha particle emitted from radium-224 is this much, and the radium of 226 is 4.78. Alpha particle emitted by radium is 5.68 mega eV. The radium is 4.78 mega eV. So the alpha produced by 224 has a greater energy than the alpha produced by 226. Okay. Okay. Said what is meant by decay constant? What is meant by decay constant? The same. What is that decay constant? The probability for a nucleus to decay per unit time. Okay. Suggest with a reason. Which of these two isotopes have the larger decay constant? Which has a larger decay constant? 224 has a larger decay constant or 226 has a larger decay constant? 224, 88 radium. Don't know, it changed to a new particle and give out alpha with energy of how much? 5.68 mega eV. The other one, that's 224. 226, how much? 226, 88 radium. Give out another daughter nucleus, we don't know what, but give out alpha, but that alpha has energy of 4.78 mega eV. So suggest with the reason, two isotope has a larger decay constant. Radium has a larger, 224 has a larger decay constant or 226 has a larger decay constant?
224.
Very good. Has a larger decay constant. Because of what? Lots of energy has been released. Okay, more energy released during the nuclear process means that substance is more unstable. Okay, if the amount of energy release is greater means during the nuclear process, the reactant is more unstable. So because 224 release more energy, therefore radium is more unstable. Therefore, it has a greater decay constant. Okay. So just why with the reason? So 224, why? Because more energy released during the nuclear process. So radium 224 more unstable, therefore large decay constant. Okay. Okay, B. In our calculation, recall back the three formulas. A equals to lambda n, n equals to n naught E negative lambda T. Another one is what? Half-life equals to ln 2 over lambda. Three formulas. Okay. So radium 224 half-life given 3.6 days. Careful, you need its days. Calculate the decay constant stating, calculate the decay constant which it is measured. Calculate the decay constant. So which formula? That one, right? So lambda equals to ln 2 over half-life. So ln 2 over half-life, you can leave it as 3.6 days if you want. So whatever lambda you get is per day. You can do that. No need to change to per second. Because here also they never put any unit. So you can write the value without conversion, you can put per day. Okay. Or you want to convert to per second also can. Okay. But I think I won't change because more work. So I leave it as day per day. Okay, next. Determine the activity of the sample radium of mass 2.24 milligram. So 4 mark. Determine the activity of the sample of 4 mark. 4 mark is a very lot. It's a lots of mark. Only difficult question they give lots of mark. 4 marks. Determine the activity of the sample of 224 of mass 2.24 milligram. How define activity? Activity is first formula. So yeah, activity is lambda n. We can find activity if you know the lambda and n. Lambda we know already. We calculated earlier. This is the trap. If you put it here per day, here must be per second. The lambda must be second. So if you put per day, then whatever value you got here, let's say x. So x divided by per day change to per second. So do what? 24 times 60 times 60 at the bottom, right? So you get per second. Then another problem is n. You must put number of particles. So how to find n? 2.24 milligram. How many particles? So your chemistry knowledge. 224 carries lots of information. So 6.02 times 10 power 23 particles consists of 224 gram. Always 224 gram. So check 2.24 milligram. Milligram is 10 power negative 3 gram. Consists of, sorry, I need to put the other way around. The X particle is 2.24 times 10 power of negative milli and negative, change to kilo, gram. So negative 3 gram. So use ratio, right? Use ratio to find your X. So what is your X? Actually, I can put N. I better put N. I'm looking for the N. So what is N? N is ratio, right? 2.24 times 10 power of negative 3 over 224 times the Avogadro constant. So you get the N, right? So that N you put here and you got your activity answer. What you need? Of course, Becquerel. Okay. This is a very problematic equation. Why? Because of lambda. You see, for this, purposely they give up here per day, and then down here, you should know you must use lambda as per second. Whenever you use A equals lambda, be careful. Okay. Any part you don't understand here too? Okay, so no questions. Yes, the others. Maybe you tried this paper. Do you have any other questions? Any part you don't understand? No. If you don't have, then I go randomly questions. If you have, you just tell me, then we can go in depth about that. Okay, because this question is halfway, let's finish it off. So we get the decay constant, then we got the activity for 2.24 milligram of substance. Now we concentrate focus to C. So C is what? Calculate the number of half-life that must elapse before the activity of the sample of the radioactive isotope is reduced to 1/10 of its initial value. Oh, calculate the number of half-life that must elapse before the activity of the sample of the radioactive is reduced to 1/10. So 1/10. 1/10. That means 1/10, 1/10 is actually what? A over A naught, lah, right? A over A naught is 1/10, lah. Reduced to 1/10 of it. So they want how many half-life? Okay, so we find the time first, lah. So A equals to A naught E negative lambda T. So we know A over A naught is the value E negative lambda T. So we find the time first. A over A naught is what? 1/10. E lambda is how much? Lambda the one you got earlier, right? You got earlier. Half-life, you know, so lambda you already got per day. But here, you know, per second. So what lambda do you want to use? Yeah. You put per day or per second? I think I go for day. I put the lambda in per day. And the time I'll get here, I'll get the time when you rearrange the time I'll get for day. Okay. So this is the time taken for the substance to drop to 1/10. Okay, left. So why I want to put day? Easy for us because half-life also given in day. So how many half-life required? How many half-life required? N half-life equals to T. So how much is the N? T over the half-life lah. So whatever day you got here, X. So X over the half-life. Half-life how much? 3.6 days. Let's divide by 3.6 days. So get the N. So this is what should be in your mind. When you read this question, you should know you're looking for the time. Find the time first. A over A naught is 1/10. Okay. So you put 1/10. So find another big problem is what unit you're going to use for the lambda. Here I leave it as lambda as per day so that I can time is in day because half-life given in day. So easy we can find the number of half-life. You confuse what unit to be used, all convert to per second. All convert to SI. You won't get wrong if you confuse. Okay. But more work. The choice is yours. Okay, any other question? Collection, Okay, so let's scroll down. Okay, different type of question. The next question, page 10. Page 10, yeah. The isotope of manganese 56 decays and undergo beta particle emission to form a stable isotope of iron 56. Manganese 56 decays, undergoes beta particle emission to form a stable isotope iron 56. The half-life for this decay is 2.6 hours. Initially at time T0, the sample of manganese 56 has a mass of 1.4 microgram. Okay. And there is no iron 56. Okay, so purely manganese 1.4 microgram and the time 0. Okay. Now what's the question? Complete to show the variation with time T of the mass of iron 56 in the sample for time T0 to time 11 hours. Show the variation with time T of the mass of iron 56 in the sample for T0 to 11 hours. So up to 11 hours, they want you to draw the graph. How does it looks like? Okay. iron 56 is product or reactant? iron 56 is the product, right? It's a product. It's a product. So how the graph going to look like? What shape? Going up or going down? The reactant should go down, right? Reactant. Product must go. Let's go up, right? Like this, right? Like a reciprocal. So ion must start from 0, right? Because ion is the product one. Okay, that's a trap. Normally we thought half-life means the graph from up go down. Yeah, it's go up, go down for reactant. Reactant decreases continuously. But here they trick us, they want us to draw the graph for the product. Start from 0. So how do you draw? The graph should goes up, but be careful. They give numbers, so you have to mark carefully. What is the half-life? Half-life is 2.6 hours. That means this also like a VL. Center is 3, 2.6 is somewhere here. 2.6 hours. Half-life happens. How much of mass beginning? Mass of ion? Mass of ion is 1.4 microgram. So we go 1, 2, so 0.2, 0.4, 0.6, 0.8, 1.0, 1.2, 1.4. So 0 going to rise by how much in 2.6?
Oh, by half of the max. Is it? Oh wait, product.
Okay, class. Can you hear me now?
Yeah.
Yeah, I got a problem with the connection. Sorry. Okay, okay, let's continue. Suddenly disconnect. Okay, so you can see the question again, right?
Yes.
Can Okay. So just now we thought how to plot the graph. So the graph should be because it's a reactant. This is a product. So 0 become how much? Become 0.7. Become 0.7. Then at a 5.2, so you 5.2 roughly, right? 5.2 here. The 0.7 should rise about how much?
By half the max.
10 point, how much? Half of 7 is how much? Half of
Oh,
7 is
11. Oh,
3.5, so 10.5, right? So around 10.5 here. So yeah, then so you have to, when you draw, don't simply draw whatever pattern you like. Okay, they're going to check the coordinates. Is it first half-life, do you reach 0.7? Second half-life, do you reach another half of it? Third half-life, even up, and so on. Okay. Okay, so this is the expected graph for IN, IN 56. Okay, next. For the sample of manganese 56, determine the initial number of manganese 56 atom in the sample. Okay, how much number of atom in manganese 56? Initial number. What formula? A equals to lambda n. I think that's the only way to find the initial number. But if you know activity, what do you know activity? You don't know the activity. What given? Or mass given. Initial mass is given what? 1.4 microgram. Then we no need to go for A equals to lambda n. It's completely chemistry. Okay. So 56 gram is Avogadro constant number of particle. So this mass is how much? 1.4 microgram. So 1.4 times 10 power negative 6 gram. How many particles? Okay, so ratio. Yes, so n equals to what? N equals to 1.4 times 10 power negative 6 over 56 times Ne. You get the number of particles. Okay. Okay, so you get the number of particle in 1.4 microgram. They're testing your conversion again. Next, the initial activity. So what is the initial activity of that substance? Now use A equals to lambda n. So you know n ready, so you can put the n. You can put the n. Lambda. Okay, lambda. Another trap. Lambda given. Oh, more work. They give half-life. Half-life 2.6 hours. So extra work. So before you use lambda n, you do what? You find the lambda first. What is lambda? Ln 2 over half-life. Ln 2 over half-life. You want to put in second or days? Half-life better you put in second. You put in second because we want to get lambda in second. So that we can use this formula. So whatever days you multiply by 24 times 60 times 60, get in seconds. Then the lambda will be in per second. So use that lambda here to get your activity in what unit? Cross-becquerel. Okay. So just substitution. Be careful with the unit. What unit you use? Any question from here? This question. Okay. So I hope you understand the flow. Initial activity A equals lambda n. We stuck to find the activity because lambda was not given, but half-life given. So we can find the lambda first. But now lambda you want to put what unit? Because A equals lambda n, requesting lambda must be in per second. So we find the lambda in per second here. So the half-life must convert from days to second. So 24 times 60 times 60 to be used to get the lambda in per second. Then we can get the answer. Another one problem or number of particle we already know earlier, so you just substitute here. Okay, so now you know initial number of particle, we know initial activity. Now we proceed further. See, determine the time at which the ratio of IN 56 over manganese 56 is equal to 9. So that means 9 is 9 over 1 lah, the ratio. originally was completely what? Originally is manganese, right? Originally was manganese. After a certain time later, of course, the manganese become what? Smaller. This is become manganese, and the balance turned to iron. So they're asking what time? They're asking what time? At what time the ratio become 9 to 1? 9 to 1. It means actually 10 parts. The 9 parts become iron, and 1 part still remain as manganese. Okay, so what formula do you use? M equals to M naught E negative lambda T. You can use that if you want because they are mass, right? Okay, this formula only works for product or reactant. This formula is for product or reactant. This formula for the reactant, right? The reactant decay. So this go for mass of manganese which is still left. This M naught mass of manganese original mass equal lambda N. So the ratio we're going to put here is mass of manganese which is left over the mass of the original mass of manganese. So original mass is how much? It's completely like 1. The mass left, how much? The manganese which is left is how much? 1 over 10, right? 1 over 10, right? 1 over 10 left, right? You see, manganese is 1, iron is 9. When iron over manganese is 9 equal to 9, that means the ratio is 9 to 1. 9 part is in iron, 1 part is manganese. So how much of fraction of manganese still left? 1 over 10, right? 1 part divided by the total part. Total part is 1 plus 9. So 9, 10. So conclusion is M over M naught, you put what? M over M naught, you put as? Anybody? 1 over 10. Right? 1 over 10, right? 1 over 10 over 1 is 1 over 10. Is equals to E negative lambda T. Yes. This is what you should write. The M over M naught must be 1 over 10. Because this formula go for reactant. Reactant means focus to manganese. The manganese originally is completely like completely is by manganese 1. But after a time t, how many manganese left? 1 over 10 manganese left. 1 over 10. Okay, 9 already convert to iron. So M over M naught is 1 over 10. So good. So we can work out the time here. Find the time when the reactant dropped to 1 over 10. Okay, good. So those who got should write here 1 over 10. Good. Understand. So 1 over 10. E lambda is what? Negative lambda. Lambda here you put, do you know lambda earlier? Of course you calculate lambda, right? Do you know lambda? Or lambda we know. Half-life 2.6. I think in the question itself we found lambda already. If it's in per second, okay, we put here per second. Lambda we put per second. Oh, you see trap here. Lambda, if you put the one you got earlier, the one you got earlier is in terms of per second. So let's say here you put per second. Then the time you're going to get in what unit? The time you're going to get is in second, right? Get second. But you see Cambridge, they want in hour. Okay, they're just testing your unit conversion massive. So once you got per second, what do you do? You just divide by, of course, hour, right? So second change to hour, what do you do? 60 times 60, so 3,600. Second divided by hour, just divide by 3,600, you get in hours. The trap here is, I think, 1 over 10. You should realize it should be 1 over 10. Correct? Okay, any part you don't understand here, guys? So quite a massive usage of the 3 equation. And the chemistry link also here, they ask about the number of particle. And number of particle, remember, the nuclear number in gram is mass of 1 mole of that substance. Or the nuclear number in gram is equals to mass of equivalent to the Avogadro constant of number of particle. Any questions, guys? No questions, eh? Okay, so yeah, the question continues. Continues. Got lots of energy like that. Give a try. Okay. You have more questions in your passes. So try to do these questions. Okay, try to understand. And at the notes here too, notes as the notes. Okay, the notes also at the back. You have questions. You can give a try and try to compare with the answers here. Try to understand the topic better. Okay. So on Monday we will be starting with a new topic. Okay. So Monday we'll be starting with the next topic. We go ahead with what? Electronic. Okay, we'll be doing electronic. So on Monday we'll start with so we're going to do electronic. Electronic, what we're going to talk about is about the op-amp. We're going to talk about amplifier. Okay. In your early studies, do you learn about amplifier? What level do you learn about amplifier? You learn about the small component of amplifier, right? Transistor.
Yeah.
You learn about transistor, eh? So yeah, it's about transistor, but we're going to talk the big brother of transistor here, called operational amplifier. Okay. One operational amplifier will consist of like 20 over transistor in it. Okay. So what is the function of transistor? Last time you learned? What is the function of transistor? To amplify signals, right?
Yeah.
To amplify signals is a transistor. Here we learned the same thing, but big brother, operational amplifier, which is a big scale of amplification. So that's what we're going to learn next class. So this is like one chip is like one operation amplifier. This chip size is around 50% of your, maybe 50 or about half of your 5-cent coin size, very small. But inside this integrated circuit, you will have these components. This is what inside the integrated circuit. So you have a lot of transistors like inside, but its function just amplifying the signal. Okay, so have some idea about this topic. We discuss on Monday.
Okay.
Any questions?
No.
No questions? Okay, so I see you back on Monday. We have about another 3 topics. We have about 3 topics. We will finish the syllabus within 3 weeks. At the background, please do your trial papers, your past years, get ready for your trial. We might have 2 or maybe 2 days for revision. So every year is like that. Just nice to be finishing the syllabus before your trial. Not only for you, all the batches like that, because of the amount of topics to cover is a lot. Okay, so I stop here. Any questions? Oh, okay, thanks. See you then on Monday.